So good morning. So in this slide data, we are going to try to go through various chapters which are tested in Math Olympiad. But what we do in this session is just be maybe 10 or 20% at most. So most of the work, you will be the one driving it. So beginning with number 3. It's a very wide chapter. It's actually a branch of mathematics on its own. But we'll try to give the key highlights that can help you to tackle mathematical problems. So I begin by listing the chapters which are covered under number theory. But the key objective is to actually attack problems. So the objective of all this session attack problems. So using simple methods and techniques. These are simply formulas. So the main chapters under number theory will begin by this introduction. So for introduction, so I begin by giving the basics on solving mathematical problems. So the key, the first main concept to solve mathematical problems is sets. So sets, so we write, and sometimes I will rotate. So a set is a collection. A set is a collection of well-defined objects. A set is a collection of well-defined objects. Collection of well-defined objects. These objects are these objects, which may be numbers. These objects, which may be numbers, letters, shapes, or anything else, are called elements, or members of the set. These objects, which may be letters, numbers, shapes, or anything else, are said to be elements or members of the set. So we use the notation. This to me belongs to or member of or an element of. So this sign belongingness sign. So we can write, for example, A And customarily, we use capital letters and small letters to write the elements. So for example, if this set A, then I can write to mean that A is an element in set A. Or I can write O is an element that belongs to set A. Or I can write this to mean that this is an element in set A. So why the notation? Why the notation? Mean. Why the notation? So what would be the meaning of this? If this means belongs to this name? Other name? So I'll give you right this. Correct. So this means does not belong to. So does not belong to, or is not a member of, or is not a member of, or is not an element of, or is not an element of. So for example, with respect to this set A, I can say, for example, X does not belong to set A, because in this listing, there's no letter X. I can say Y does not belong to set A, because we don't see any element Y in this listing. So more on sets will be covered in basic mathematics when you transit to the next level, but ours is to get the basics. So special number sets. Okay, special number sets. So, but then when we go to school, the first level in preschool, do we start counting from 1, 2, 3, or 0, 1, 2, 3? The first time we interact with numbers. Do we start at 0 or do we start at 1? Do we start 1, 2, 3 reciting, or 0, 1, 2, 3? Huh? We start from 1, okay? So the first stage is called counting all natural numbers. Natural numbers. So natural numbers we abbreviate by this sign, bold N, and these are simply numbers which start from 1, 2, 3, 4, 5, 6, etc. So the numbers 1, 2, 3, etc. are called natural numbers. And when you do addition of natural numbers and multiplication of natural numbers, you get the same set natural numbers. So we can say that the set of natural numbers closed under the usual addition and multiplication. Because you pick any two numbers here, you add, or you pick two numbers in this set, you multiply, get a number within the same set. But when it comes to operation of subtraction, if you pick any two random numbers here and you subtract, you'll not be guaranteed to get a number within the same set. For example, say 1 minus 3 is not a number within. Or say 1 minus 1 is a number which is not within this set. So that gives us the second set of numbers. So we call them whole numbers. And whole numbers are abbreviated by whole W. And now this we start from 0, 1, 2, 3, 4, 5, etc. That is how we call the set. How do we go to the next? That's what it is. How do we move to the next slide? Yeah. Okay. So number 3. Okay, so also addition and multiplication is also closed on the set of whole numbers. But subtraction is also not always the case. If you take two whole numbers and you subtract them, it's not always the case that you get another whole numbers. So we have the next set of numbers we call integers. And integers, we use both W, both Z. So these are numbers 0 plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, etc. So then now for the set of integers, when you do addition on this set, you get a number within the same set. So set of integers is closed under addition. When you take two random integers, multiply them, you get another integers. Also, when you take any two random integers and subtract them, you also get another integer. But then now we have a problem on division. For example, if I pick say 2 divided by 5, so it's a number which is. So it tells us that if you stop at the set of integers, then you still have some problems on doing the normal operations. But under integers, there are those which you call positive integers. So positive integers, we abbreviate by Z plus. These are 1, 2, 3, 4, 5, 6, etc. So when you start counting from 1 to infinity, then those are positive integers. And they what we call negative integers. So negative integers, we put a negative on top of Z to be negative. So this say negative 4, negative 3, negative 2, negative 1. Those are what we call positive and negative integers. And then, okay. Then C is what we call non-negative integers. So non-negative integers 0, 1, 2, 3, 4, 5, etc. And there's what we call non-positive integers. So these are say minus 5, minus 4, minus 3, minus 2, minus 1, and then 0. So there's a difference here. So non-negative does not mean positive. And non-positive does not mean negative. So the number 0 is neither positive nor negative. So if you want to take care of 0, you'll either refer to non-positive or non-negative. But when you say positive, then 0 is not counted. When you say negative, 0 is also not counted. So when you are responding to Olympiad type problems, you have to be very careful not to make a confusion of the terms positive and negative. So when you purely say negative or positive, 0 is not taken into consideration. But if you talk of non-positive or non-negative, 0 is part of that set. And then this is what we call rational numbers. The rational numbers, we abbreviate by bold Q. So just from the name itself, rational comes from the word ratio. So a rational number is any number obtained by taking ratios of two integers, say A and B. So we write this A over B, where B is not 0. So if you want to be more serious, this statement can be framed as a set of rational numbers is a set of all elements of the form A over B, such that A and B are integers, then this B is non-zero. Okay, sometimes we add that the GCD of A and B should be 1, but then a number like 10 over 12 is still a rational number. So we can either add that to fiction number. So numbers which are of the form A over B, such that. So in this statement, columns, or sometimes we use a straight line, is read as such that. So this is read as such that. So when I open brackets, these curly brackets, this form, this means a set. So this set of all elements A over B, such that A and B are integers and B is non-zero. So examples of numbers in this set is like 4 over 5, say 6 over 7, 11 over 13, 19 over 23. Then a question can be is 0.2 0.2 rational. True or false? So why? Why? Is it a rational number? What is it? Yes? Okay, not. Is it a rational number? Why? 2 over 10. is integer 1/5. So the answer is 2. And then 0, and I say that 0 is a rational number. Yes or no? Is 0 a rational? Why? Is 0 rational? Why? Okay, maybe you are not happy that way. Let me say 10. It's 10 a rational number. Why? Can be written as 10 over 1, okay? 10 over 1 is a ratio of 3. And 0 when you make, remember, don't be confused by here. This is actually common sense in a fraction. But 0 cannot be in the denominator. That's why I say this one, B should not be 0. We are not saying that we are excluding 0. We are saying that it is a fraction, but the denominator cannot be allowed to be 0. So 0 can be written as 0 is the same. Say 0 over 1. 0 is an integer, 1 is also 1. So the only problem is when you write things on, say, 1 over 0. That's where the mistake are the problems. But 0 is also part of this set. So before we move to the next set, if we are to relate what we have covered so far, is it true to say that all rational numbers are integers? True or false? All rational numbers are integers. If I confirm that statement, all integers are rational numbers, becomes true, okay? And if I say all natural numbers are rational numbers, true or false? All natural numbers are rational numbers. It's true, okay? Good. So next, this number 5. So there's what you call irrational numbers. So irrational numbers, we use Q, but we put a bar on top of Q. So irrational number is simply any number that is not rational. Any number that is not rational. Actually, the opposite of rational numbers. Any number that is not rational. So in simple terms, we mean that it's a number which cannot be written as a ratio, A over B, where both A and B are integers and B is 0. So a number which is not rational is irrational. So e.g., a number like root 2, a number like root 3, a number like root 5, E and 5. This is where I may be destroying some careers from where you're coming from. So when we are doing area or dealing circles or area or circumference or circle, we usually told that the exact value of pi is 22 over 7. Then we write this example. Believe this is false, huh? In this class. When you go back to where you came from, then it is true. But pi is not exactly the same as this fraction, 22 over 7. So when you write 22 over 7, so 22 is an integer. 7 is also an integer. So then now, for the first 22 over 7, this number will actually be in the set of rational numbers as per our definition. Okay? But then now, the exact value of pi is pi. It's not 22 over 7. So the correct way of writing that statement is to write this. So when you write equal sign, and I put 2 dots, this means approximately equals to. So when you are given pi in the notation form, this symbol here, it is approximately equal to 20 over 7. Note that it's exactly equal to 20 over 7. So pi is 20 over 7. Then this number E, which will hit at later stage, which has a rough value of 2.7 something, is also that numbers in this set here cannot be written as quotient of two integers. So when you write 20 over 7, it is a rational number, but it's not exactly the same value as pi. When you are doing the classification, get that to apply that pi, the exact value of pi is pi notation form, and then 20 over 7 is an approximation. That's why when you're responding to a problem in Olympiad, which involves application of this pi, say you are getting area or you are getting perimeter of a circle, and they tell you to write the angle in that form, you don't replace pi by 20 over 7. You leave your answer in terms of pi. Yeah, that should be very simple. So then, is it true to say that all rational numbers are true or false? All rational numbers are false or true? If I converse, all irrational numbers are rational numbers. If I say all integers are irrational numbers, same false. Okay. So know that rational and irrational is day and night. There's no number which is both rational and irrational. So when there's this notation we call intersection, so usually write Q intersects by Q is empty. So when you write this pi means empty, there's nothing, it's a set which has no element. That there is no number which is both rational and irrational. That's why I'm questioning you that what you say pi is equal to 20 over 7 is not true, it's just an approximation. So you can't use it as an example to justify your argument that pi is 20 over 7 and it's also when you write in notation form is rational. So there's no relationship between it, just approximately equals to. So there's no number which is both rational and irrational. So this is a standalone set. All the sets that we're discussing from here, that numbers. Then this 6 or 7? 6. So real numbers. So the set of real numbers we abbreviate by this bold R. I is very easy set to define. It's simply a number which is rational or irrational. Any number which is either rational or a real number. And probably all the numbers you know are real numbers. So all the examples of all the sets that we have discussed. So examples here, say 1, 0, pi, e, 0.3, 16, 0.0, 0.0036, etc. All those are real numbers. Any number that is called a real number. Even your phone number, if you have one, it's a real number. And then lastly, which probably will not cover, is what you call complex numbers. So complex numbers we abbreviate by C. So bold C. Complex numbers. And these are numbers which can be written in the form A plus BI. Numbers which can be written in the form A plus BI, where A and B are real numbers, and I means square root of -1. So numbers which can be written in this form, A plus BI, where a and b are real numbers and I is square root of -1, are called complex numbers. So for example, 2 plus 3i, 6 minus 4i, 5 plus 3i, a half minus a half I, etc. So for example, if you are asked to solve for x squared plus 4 equals 0, then we'll have this one as x squared equals to -4. And then the opposite of square is square root, so square root of -4. And then you can write these are square root of 4 times -1. So that's what the value of -4. So then you can have this as square root of 4 times square root of -1. And square root of 4 is plus or -2. And then square root of -1 is r. So the solution here is 2r. So if time will allow, we'll do some problems on that given set. So that will just the special number set that we'll be using. So more definition. So divisibility. Now we are not actually going to narrate the divisibility test of 2, 3, and 4. Okay, it will be a waste of your time. So we'll start by defining the divide operation. So divide. So let's now at this point now we know those special numbers. So then say let a and b be two integers. So then when I write that one, that should make sense. So let a and b be two integers. So we say that a divides b. We say that a divides b denoted by so you write a straight line, b. This is a vertical line. So this means a divides b. If they exist another integer c such that b is equals to a times c. So that's what we say a divides b. So for example, I can say 2 divides 6, since 6 can be written as 2 times 3. Now, don't mean multiplication. So this is not 2.3. This means 2 times 3. We can also say 3 divides 15, since 15 can be written as 3 times 5. So that's what we mean by divide operation. So this is a straight line. I was just learning about. So Do not confuse A divide B with A over B. Two don't mean the same. So you are dividing A and B, here you are saying A. What is the meaning of the notation? Yes, this means A does not divide B. For example, I can write 2 does not divide 7. For example, 2 does not divide 7. Since there is no integer C such that seven can be written as 2 times 6. So when you for this something to make sense, then this must be a decimal. This must be so 2 does not divide 7. So that's those are the basics. Still under divisibility, there's what we call the Euclidean algorithm. Division algorithm. Actually, sometimes there is no distinction between the Euclidean algorithm and division algorithm. Sometimes we give the same interpretation of the two terms. So we'll begin by, so THM will mean theorem. When I write THM, I mean theorem. So theorem, we state the division algorithm. Okay, I'm sorry, my screen is connected off. You know, these are the top points of the country. I'm sorry. Maybe tomorrow I will fix them. Don't worry. So division algorithm. So for every pair of integers, so the statement for this theorem, for every pair of integers A and B, right? For every pair of integers A and B, there exists, for every pair of integers A and B, there exists distinct sometimes we say unique. For every pair of integers A and B, there exists distinct or unique integers Q and R. There exist unique integers Q and R called the quotient, called a quotient and the remainder respectively, called a quotient and the remainder that satisfy with so for every pair of integers A and B, there exists unique or distinct integers Q and R such that A is written as B, Q plus R. So this R is the remainder, and then the remainder, the absolute value of the remainder is between 0 and B. So it can be exactly equal to 0, meaning there's no remainder when you're doing the division, but it's strictly less than this other number, B. So for example, for us to appreciate this one, if I give you, say, 12 and say 5. So I have 12 and 5. I can write 12. So this is my A, this is my B. So usually we do this, then you put 5 here. So closest multiple of 5 to 12. So closest in the sense that it is exactly equal to 12, but strictly less than 12. 10, okay? So how many times? So 2. So difference, I get 2. So this number is less than the divisor part. So it becomes our remainder. So we'll have this as 5 times 2, then plus 2. So this is our quotient, and this is our remainder. Then if I give you, for example, say A to be 15, B to be 8. What will be the P1 R? Can you get to the number? What is P1? I don't know. Questions? And that is next one. Here's one, then add 7. Correct. Then so Euclidean algorithm, another theorem. So we say for natural numbers A and B, for natural numbers A and B, the division algorithm for natural numbers A and B, the division algorithm states that A equals to BQ plus R. So for natural numbers A and B, the division algorithm says that A can be written as BQ plus R, where Q is a quotient, R is a remainder. Then GCD of A and B, GCD of A and B is the same as GCD of B and R. So the division algorithm helps us to get a Q and R. And then when we narrow down to Euclidean algorithm, it allows us to get the GCD of the original numbers A and B. So the GCD of A and B is the same as GCD of B and R. And then with respect to this theorem, so we can obtain a process or a way of obtaining GCD of two numbers A and B. Corollary. For two natural numbers A and B, and please know that if you remember what we previously defined, then if I don't want to use the word natural number, I want to use it, if I don't want to use it, so natural numbers is equivalent to such. If I use positive integers, okay? Yeah. So when someone says natural numbers and other person says positive integer, they mean the same. Yeah. So for two natural numbers A and B, with A greater than B, for two natural numbers A and B, with A greater than B, to find the GCD of A and B, to find the GCD of A and B, we use the division algorithm. 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 This would mean that A is B Q plus R. Then we usually restrict that but by definition, if you have any two natural numbers of positive integers or even integers in general, this relationship A and B are related by this A equals to B Q plus R. Now call this P1, call this R1, call this R1. So that's the first question and that's the first remainder. So what we should do in the next step, the role of A is now taken by B. So you write B. And the role of P1 is taken by R1. Then this we get a new quotient and a new remainder. And the restriction here is R2 should be strictly less than this. R should be strictly less than R1. Okay, good. Then the next step, the role of A will be taken by R1. The role of B will be taken by R2. Then this generates our Q3 and R3. The condition here is that R3 should be strictly less than R2. Then the next step, A will be taken by R2, B will be taken by R3. Then this generates our Q4 and R4. Then the restriction, R4 should be strictly less than R3. Then this process continues up to, I'll have Rn minus 2 equals to Rn minus 1. So can you tell me if you're following? If you are doing the same process. N, correct. And then what will be the subscript of R? R, N. And then what should be the restriction? 0 is less than Rn, which should be strictly less than Rn minus 1. Good. Then next we have Rn minus 1 equals to Rn Qn plus 1. So this last step, the remainder is 3. Then we stop. So when you do the change the roles of A and B, to reach a point, it must always reach a point. That's always guaranteed. It must reach a point whereby the remainder will be 0. Then when you reach that point, you stop. So then the GCD of A and B with this value Rn. So the last non-zero remainder is what gives the GCD of the two numbers, A and B. So as an example, use Euclidean algorithm to find GCD of 110 and 490. These are appetizer anyway. So I want you to tell me what will be our A. What will form our A and what will form our B from the statement, the corollary. A will be 490. That's without loss of generality, is 490 because we say that A is greater than B, okay? Yeah. So here, A is 490, B is 110. Good. So we write 490 is equals to 110 times. So the smallest closest multiple of 110 to 490. 440. So 110 divided by 4. Remainder is 50. Yeah. So this actually is in argument with the division algorithm because we say that the remainder must always be strictly less than B. Okay. B is 110. So then what takes the role of A? 110. Then B will be 50. So the closest multiple of 50 to 110. So 2, then the remainder 10. So A will be taken by 50, then 10. So for the question, 5, remainder 0. So immediately you get the 0 remainder, you stop. So then the last non-zero remainder becomes the GCD. So GCD of 110 and 490 will be given by 10. So that's another thing. So can you work on this? GCD of 6 and 64. Find the GCD of 36 and 64 using division algorithm. Do the process correctly because we think so please know that now when you are, what you are preparing for very important. So the answers are not instant, not really important. What matters. So whenever you hang up on what answer you getting? So now everyone has to pick. So index 2. Index 1 are this spoken? Yes, you have answers. So index 2. The answer is 4. Is everyone having 4? Okay, good. So next theorem, the Zeus theorem. The Zeus theorem is actually built up from the division algorithm that helps us to find the or to express GCD in terms of the number. So for any two natural numbers, A and B, for any two natural numbers, A and B, they exist two integers, X and Y, for any two natural numbers, A and B, they exist two integers, X and Y, such that AX plus BY is equals to GCD of A and B. So for any two positive integers, A and B, there always exist two integers such that the GCD can be written as a linear combination of two numbers. So as an appetizer, express GCD of 110 and 490 in terms of A and B. This GCD of 110 and 490 in terms of A and B. Okay. Oh, okay. In terms of this, this is 490, and then this B is actually 110. Okay. So this is what you do. So the first thing actually you have to repeat the whole process. We say that now we'll have A here is 490, B is 110. So we have 490 equals to 110. That's 110 by 4 plus 50. That was the first step. And then the second step, we say that 110 take the role of 490 and then 50 by 2 plus 10. Then we have 50 equals to 10 times 5, then plus 0. Then you say that once we have that, then this is a GCD. So this is line 1, this is line 2. So we view these numbers as variables. So we now retransform from 2 where you have the GCD. We'll have 10. So you work out bottom up. So from the GCD now going up. So you write this 10. It's like make 10 the subject. And then we have 110 minus 50 times 2. Don't open this to give you 100 because we view these numbers as variables. So leave it in the way they are. Then now from the previous time, 50 can be written as 490 minus 110 times 4. So this is the same as 110 minus. So instead of 50, you write 490 minus 110 times 4. And then we had times 2. And now remember, this is just a product. So there's no mistake of me putting these 2 here. And then I delete it from here. So this is what you have. Now, in the usual way, so we have here minus 2 times 490 will give me minus 2 times 490. Then minus 2 times minus 4 times 110. So minus minus is plus. So how many 110s are there? So these 2 times 4 times 110. So 110 is now like the variable here. Like I have minus 2 times minus 4x. So x here is this 110, okay? So I'll have, so we have 8 110s. And these are how many 110s? So when we put them together, 9. So therefore, this GCD of 110 and 490, which is 10, is given by minus 2 times 490 plus 9 times 110. So can you confirm that? What is minus 2 times 490? 9 minus 980, okay? And then 9 by this, 990. You clearly see that actually get. So this is the solution. So we'll share with the hands on like the previous question also, you can also express the same in terms of the GCD. So the next, if you are able to do the division for numbers, we can also do the same thing for polynomials. So the division algorithm, next line, the division algorithm also works for polynomials. The division algorithm also works for polynomials. And then we skip a line and say, if A of x and B of x are 2 polynomials, if A of x and B of X are two polynomials, then we can find a unique quotient. Then we can find a unique quotient, Q of X, and a unique remainder, R of X. I said if A of X and B of X are two polynomials, then we can find a unique quotient, Q of X, and a remainder, R of X, such that A of X is given by B of X times Q of X plus R of X. And then the restriction here is that degree of R of X must be strictly less than degree of B of X, or this remainder polynomial R of X must be equal to 0. So this is what you have. And just to appreciate, remember a polynomial is a function, so later on we'll actually delve into functions of the form an x power n. Okay. Yeah. Function of the form a naught plus a1x plus a2x power 2 plus a3x power 3 plus a4x power 4 plus an x power n. So if an is not equal to 0, then the degree is of degree n. So the coefficient and all these numbers, a0, a1, a2, a3, a4, up to an, are in our case subsets of real numbers. So they're either real numbers or rational numbers, or they may be integers. So a0, a1, all the way up to an are in a set of real numbers. So one thing I have to make clear here. So for example, if I have, okay, maybe just a few examples. So if n is 1, then I'll have, if n is 0, I just have a0. These are called constant polynomials. So if n is 0, then I'll only have a0, and then I call it a constant polynomials. If n is 1, then I have a0 plus a1x. These are called linear polynomial or functions. So for example, I have 2x plus 3, 3x plus 4, I have x minus 3, say 2x or 3x minus 1, etc. Those are numbers of linear. If n is 2, then I'll have a0 plus a1x plus a2x squared. These are called quadratic function or polynomials. So for example, if I have 3x squared plus 4x plus 9, have 3x squared plus 9, have 6x squared plus 3x. Say I have x squared minus a third, etc. If the highest power is 2, I have that. So when n is 3, we have a0 plus a1x plus a2x squared plus a3x cubed. What will be the name for this? Cubic. So these are called cubic polynomials of functions. And then when n is 4, so cubic examples for maybe 3x cubed plus 9x squared plus 4x plus 3. And another thing that is what matters is for cubic, what governs cubic polynomials of functions is coefficient of x power 3. So that's what matters. These other terms can as well be allowed to be 0. This cannot be 0. And then when n is 4, what name do we give to that polynomial? Quartic, correct. So when n is 4, have what we call quartic polynomials. So for example, 4x power 4 minus x cubed plus 9x squared minus 3x plus 10. That's an example of a quartic polynomial function. Now when n is 5, what special name do we give? Quintic, yes. So quintic polynomial or function. So and what governs is that the coefficient. What matters? 0. So others can be allowed to be 0. So just in the same way, in general numbers, they can also apply division algorithm for polynomials. But then here, we know what we call long division to do the division. So NB, we can find Q of X, we can find Q of X and R of X using long division. Using long division for polynomials. Using long division for polynomials. So we can give an example. Calculate Q of R. Calculate Q of R and R of X such that A of X equals to B of X, Q of X plus R of X, where A of X is a polynomial x power 4 plus 3x power 3 plus 10. And then the B of X is given by x squared, then minus x. So find Q and R of this given polynomials. There's a very easy exercise, just the same way. If I give you my A is 12 and my B is 5, we write 12, then you write this division sign, and then you put 5 here. And then we ask ourselves, what is the closest multiple of 5 to 12? And then you say 10. Then 2 minus 2, this becomes your remainder, this becomes your quotient. So we have the same manner. Only that now, when you are dealing with polynomials, these things we are calling closest multiples now, what you need to multiply by B of X so that the highest power of X can be the same as what we have A of X. So you write this division sign, then Bx power 2 minus X, and then X power 4 plus 3X cubed plus 10. That's the usual way, the way we are doing it. So the degree of a polynomial, the highest power of X in the polynomial. So these are degree 4 polynomial because the highest power of X is 4. These are degree 2 polynomial because the highest power of X is 2. So what should I multiply by this X squared to get X power 4? X squared. So you write here X squared. Then X squared times X squared is X power 4. X squared times minus X, give me minus X cubed. So that's what I'm. In a similar manner, I put a line here. Then I subtract. Then remember, when you're subtracting polynomials, you subtract like terms. So X power 4 minus X power 4 is 0. 3X power 3 minus X power 3. Minus, this is plus, okay? So this will be 4X power 3. Then you bring down this term. So this now a cubic polynomial. This is divisor is quadratic polynomial. We can't stop because now is in this context what we have done at this time. This falls in the place of the remainder. Is the divisor, is the quotient. But the restriction for polynomial division is that the degree of the remainder should be strictly less than the degree of the divisor. So we still do the division next time. So what should we multiply by to get 4? So 4x. So 4x by this will be 4x power 3. 4x by minus x minus 4x squared, okay? Same manner is subtraction. Remember here, there is no term with x squared, but you can always force it there. I can have this is plus 0x power 2. There's no mistake by doing that. Part of the polynomial. So 4x cubed minus 4x cubed, now we do away with terms with power 3. And then 0x squared minus 4x squared. Minus is plus. So we'll have 4x power 2, then bring the 10. So degree of the new divisor is a new remainder is what? 2. Degree is this strictly less than? So they are the same. So you have to repeat the same process. So what should we multiply by x squared to get 4x squared? 4. So plus 4. So I'll have 4x squared and then minus 4x. So you still do the subtraction. So 4x squared minus 4x squared is 0. Now we don't have terms with power 2. And you can always force an x term to be in this term, so that we have 0x minus 4x to give us 4x. Then you bring 10. So what governs our stopping point is the degree of the remainder. So what the degree of this polynomial? 1. This is 2. So this is more than this, okay? So then you stop. So therefore, Q of x will be given by x squared plus 4x, then plus 4, and R of x will be given by this polynomial here, 4x, then plus 10. And you can actually see that if check that if we write in this form, we have x power 4 plus 3x cubed plus 10. Our b is x squared minus x. What you're getting as our q is x squared plus 4x plus 4. And what you're getting as our remainder is 4x plus 10. So now that if you want to expand these two brackets and you add this, the simplification will give you the same thing. So skip a line. So the structure on how to deal with this polynomial is the same structure that how we deal with numbers, the same structures we deal with the polynomials. So there's what we call how to find GCD of two polynomials. So put it in the form of a theorem. So for two polynomials, A of x, for two polynomials, A of x and B of x, for two polynomials, A of x and B of x, then like this. Okay, just as a disclaimer, when we write this, okay, maybe this. Let's note that these are square brackets. Means polynomials whose coefficients are integers, rational, real, and complex numbers respectively. So then when I'm writing this a of x, b of x, and this mean that these are polynomials whose coefficients are rational. So that's what it means. So this means polynomial whose coefficients are purely integers. This is a polynomial whose coefficients are purely rational numbers. This is a polynomial whose coefficients are pure real numbers. This is a polynomial whose coefficients are pure complex numbers. And what you're calling coefficients and this, when we define a polynomial, these values A0, A1, A2, up to AN are what we call the coefficients. So here it means that now we have two polynomials can be such that any of the coefficients in the polynomial is of the form of a ratio. So for any two polynomials which have rational coefficients like this, they exist a unique quotient and remainder. They exist a unique quotient and remainder Q of x and R of x. There exists a unique quotient Q of x and remainder Q R of x such that I can write A of x as B of x times Q of x plus R of x such that degree of R of x is strictly less than degree of B of x, and GCD of these two polynomials, A of x and B of x, is the same as GCD of B of x and R of x. That GCD of two polynomials can be obtained by doing the division algorithm. And so the extension that we did can actually be, we can also extend the division algorithm to obtain GCD. It's exactly the same process we explained, that you do the same process, but where there's A, you write A of x. Now it's a polynomial. Where there's B, you put B of x. Where there's Q, you put Q of x. Where there's R, you put R of x. When you do the extension, you can as well get the GCD. But now here, unlike for the case of numbers, there's a restriction. By convention, so not by convention, GCD of two polynomials, by convention, GCD of two polynomials is chosen to be a monic polynomial by convention. The GCD of two polynomials is chosen to be monic polynomial of the highest degree, monic polynomial of the highest degree, that divides both polynomials. Monic polynomial of the highest degree that divides both polynomials. So monic polynomials, or simply monic, that's the new term. Monic means the leading coefficient is 1. Now, when you say leading coefficient, mean that now, once you have specified the degree of the polynomial, then if you say it's a degree 3 polynomial, then the term would execute the coefficient must just be 1. So when you do the whole process that you've done, but remember, you give the answer as monic. So example, find the GCD of x find the GCD of x power 4 plus x power 3, x power 4 plus x power 3 minus 4x squared plus x plus 5 and x power 3 plus x squared minus 9x minus 9. So what will be our A of x by default? Of x will be the polynomial starting with x power 4. That's the highest degree, okay? And then our B of x will be the one with x power 3. So can we do the first step of long division and tell me what will be the quotient? Step 1. The first step. Or the Q in the first step. It's very easy to specify the Q. That means that now when you're doing the first step of division, what matters are the highest powers of the degrees of the polynomials. So the first one is x power 4, the other one is x power 3. So when you divide, you get x power I have I touched. Why? That's someone I need to press. Oh, let me see. So the first Q1 is, what is your Q1? X, correct. Q1 is X. Then our R1, 5, x squared plus 10x plus 5. That's the first step. So then our new A of X will be, next step, our new A of X. What be? You don't need simplify. So the step 2, our A becomes B, okay? And B in this case was X power 3 plus X squared. What is our new A, okay? What is our new B? Our new B? Our new B becomes step 2. New B becomes a R1, okay? 5X squared plus 10X plus 5. So can you get Q? 2. Get So what is our Q2? When you divide Q2, plus what you are doing. So simply you are now. So what you have inside the division side is X cubed plus X squared minus 9X minus 9. You are dividing by 5X squared plus 10X plus 5. So what will be the quotient in that division? Maybe the only question you can try at the end of this session. So what is our Q2? Huh? If you're able to get Q1, it's actually the same thing, the same process you have done to get Q2. One over 5X. That's the only one? Yes, 1 over 5X minus 1 over 5. Then what will be our R2? What is the value of R2? I don't know. So what will be the R2 of the leaders? R2? We are almost stopping for a few minutes. That shows that you actually are the one to derive now the process. What is R2? R2? Remember, the degree of R2 should be strictly less than our R1. So it should be a polynomial less of degree less than 2. Got it? Correct. Negative 8x minus 8. Good. So that's that step. So you write the relationship. And then what will be now our new A of X? So that step. our new A of X. Our new A of X. 5x squared plus 10x plus 5, correct. And then our new B of X. Our new B of X. Okay. Our new B of X. Just do the normal long division. Our new B of X. So remember, B of X in this step with the previous R value, okay? So what is the B of X? Negative 8x minus 8, right? So can you now divide those two columns? So our new Q of X, now that's Q3. Q3 will be our new Q3. Minus 5 over 8x minus, and then R value 0. So then you stop, okay? So what is the previous non-zero remainder polynomial? Minus 8x. So what is the GCD? What is the GCD? What is the GCD now? What is the GCD now in that case? GCD becomes, that is a point your high school math teacher. For those who have just finished their KCSE. What will be the GCD now? Well, actually, that's we have found 0. So what is the GCD? Right? Minus 8x minus 8. Let's vote. Those who support that answer? Trust your instinct. So those who support. So 1, 2, 3, 4, 5, 6. Okay, the others, which answer do you have? So if you are not accepting that, which answer do you give as the GCD? The next one, what's the answer? X. Okay. Those for X. So I have both. And then let's what option? What do you have at the GCD? Minus X minus 1. X plus 1. You are very serious. So why do you think they are wrong? Your answer is correct. Okay, that's a correct answer. Why are they wrong? Good. That's what is going to separate. So remember, pay attention to teachers. And anything that we math teachers do in class, we don't know how to perform. So everything we give is so we are doing a given morning. So I want you to have you have actually be here. So then X. So it's different from the way the balance for normal to keep money. So from minus you have money for long. So consume that I think so find the GCD find the GCD of x squared minus x plus 1 and 5x. Find the GCD of x squared minus 4x plus 1 and 5x. If they call us so it's already like it. So when we so when I play but unless they come then we can change it. So if you don't so this happens how many. Remember you have to have so what is your P1? Step 1. P1 is it? 1 over 5? Huh? Minus 4 over 5. Then what is our R1? Huh? 1. I really want telling me if we expand and then we connect x squared minus x squared. You know what is happening to this division algorithm is that sorry, this thing cannot. So when you write A equals to B, Q plus when you so I use so when is the R1? This one. I don't know why I say okay, good. Is it true that the next okay. Then another comment. This was does not mean that prove that for natural number prove that for natural number prove that for natural number the fraction prove that for natural number the fraction then one everything divided by 14 if reducible is irreducible. Also, 1n plus 4 divided by 4. That's 14n plus 3. Okay, now, for example, when we say that a polynomial is distributed in the which is as good as saying that there's no other common factor between the numerator and the denominator. If you are able to convince the GCD of those numbers, then that's good. So it's as good as taking that GCD of those two numbers, without any other number. So the moment you say you use the mean that any part. So in terms of this part, the two numbers. Since one any part. So can you find the GCD of those? Find the GCD of those. For those two. I hope you are seeing enough to know that. So that's not been like for you to see if a polynomial is another. So can you find it? So these are just for one n plus theta in the variable n. For 10 n plus 3 is also. Convince me if what is the reason. Okay, maybe we can. So thank you. That's the first session. So when you come back, we'll pick it from there.